Dear students, in this session we will discuss about Raman amplifiers. Before going to the details of fiber Raman amplifier, first of all let us see what is Raman scattering, because the basic principle behind the Raman amplification process is Raman scattering. So first of all let us see what is Raman scattering. You know that there are different types of Raman scattering. One is spontaneous Raman scattering and other is stimulated Raman scattering. Spontaneous Raman scattering was discovered by Sir C.V. Raman, and in the case of spontaneous Raman scattering, a small portion of the incident light is transformed into a new wave with lower and higher frequencies. And this transformation is because of the interaction of the photon with the vibrational modes of the material. So in the case of spontaneous Raman scattering, basically it can be observed in any type of material, and here if the scattered light is studied by irradiation of the medium by an intense monochromatic beam of light with a spectrometer, and it is observed that the scattered light will show new wavelength in addition to the original wavelength. Suppose the incident wave has some wavelength such as lambda 1, then the observed light after scattering will have a different wavelength, and the wave which irradiates the material is called pump wave. Suppose there is a material, and when the light wave is incident on that material, and that light will be scattered due to the incidence with that material, and the scattered light will contains different wavelengths, and the light wave which irradiates the material or incident on the material is called the pump wave, and the wave with the lower frequencies after the scattering are called Stokes waves, and the waves with higher frequencies which is produced after scattering are called anti-Stokes waves. That means due to Raman scattering, two types of waves are produced. One is Stokes waves, other is anti-Stokes waves. And the Stokes waves have lower frequencies and anti-Stokes waves have higher frequencies. And usually this scattering occurs due to the vibrational modes of the material, and the wave which is used to incident on the material is called a pump wave, or which that means the wave which irradiates the material is called the pump wave. The intensity of the Stokes waves is many order of magnitude higher than the intensity of the anti-Stokes waves. And let us see the frequency distribution of the pump, Stokes and anti-Stokes waves. See, you can see the wave which is used to irradiates the material is known as a pump wave, that is it is the incident wave. So when this pump wave is incident, that means this pump wave has a frequency Fp. Then when it is incident on the material, then it will be scattered into different directions. So it will produce Stokes waves and anti-Stokes waves, and the Stokes waves has a frequency Fs. See, Fs is, you can see that Fs is lesser than that of Fp, and here anti-Stokes waves have higher frequencies. So that means anti-Stokes waves have a frequency Fa which is higher than that of Fp. Next, we can see the generation of the Stokes and anti-Stokes waves. New frequencies are generated due to the energy exchange between the photons and the material molecules. That means I have already said that this scattering or generation will be takes place due to the vibrational modes of, depends upon the vibrational modes of the material. So we have to go to the details of the energy diagrams of the material to understand the concept. So let us see. See, this is the energy diagram of a material, and it should have different levels such as ground level, intermediate level and virtual level. Once, suppose in the case of Stokes generation process, all the electrons will be in the ground state at thermal equilibrium, or the electrons or carriers will be in the ground state. In the Stokes generation process, suppose we are giving a pump signal to the material, then that pump energy will be absorbed by the materials. Suppose we are saying that pump energy is incident photon of energy. That means in the Stokes generation process, incoming photon of frequency Fp See, Fp is the pump frequency, right? Fp excites the molecules from the ground state to the virtual state. And when it reaches the virtual state, the molecule returns to the intermediate states. So, due to this returning, it will, that means here, this is at a higher energy level, this is at a lower energy level. Due to the returning, some energy is released. So, that energy corresponds to a particular wavelength or a particular frequency. So, the molecule when returns to the intermediate state from the higher energy level, it releases a photon. So, we can say it is a Stokes photon of frequency Fs. So, this is clear. From the ground state, when pump frequency is given, that pump frequency is absorbed by the carriers in the ground state, and they will be go to the virtual state where it is unstable, and it will go to the intermediate state again, so that it will releases another frequency of photon. That frequency is corresponding to Stokes frequency. So, we can say it as a Stokes photon of frequency Fs. Here you can see that the energy difference between the virtual and intermediate level is smaller than the energy difference between the ground and the virtual level. See, you can see that the energy difference between these two levels is smaller than the energy difference between the virtual and the ground level. Right? So, the frequency of the Stokes photon is lower than that of the incident photons. You know that energy will be equal to h into nu, that is Planck's constant into frequency. That means energy and frequency are directly proportional. So, here the energy difference is lower, so the emitted photon will have a lesser energy. That means it will have a smaller energy comparing to that of the smaller frequency comparing to that of the incident frequency. So, this is the Stokes process. And next we can say, suppose the incident photon is, if there are carriers in the intermediate level, and if we are giving an incident photon, that is pump energy having frequency Fp, and if that Fp is that energy or pump energy is absorbed by the carriers or electrons in the intermediate level, they will go to higher energy level, that is at a virtual level, and where they are not stable, and they will return to the ground level, so that they will emit a photon. Suppose that means they are going from a higher energy level to the ground level, so the excess energy is released in the form of photon, and that photon energy or photon that wave is corresponding to a frequency Fa, that is anti-Stokes photon. That means in the anti-Stokes generation, the incoming photon of frequency Fp excites a molecules from or electron from the intermediate state to the virtual state, and the molecule returns to the ground state releasing an anti-Stokes photon, and its frequency is F or Fa. And here you can see that the energy difference between the virtual and the intermediate level, and this is the starting process, the energy difference between the virtual and the intermediate level is smaller than the energy difference between the ground and virtual level. That means here the energy difference is higher. When the energy difference is higher means the frequency corresponding to this energy difference will be higher. So, the emitted anti-Stokes photon will have a higher energy comparing to that of the incident pump energy, right? That means F will be greater than Fp here. So, in the case of Stokes frequency or Stokes photon, Fs is less than Fp, and in the case of anti-Stokes photon, F is greater than Fp. That is the concept between the behind the generation of Stokes and anti-Stokes waves. So, but you know that in the equilibrium state there will not be any other, there will not be much electrons or carrier or molecules in the intermediate states. So, the chance of production of anti-Stokes photons is lesser comparing to the production of Stokes waveform. Okay. The anti-Stokes waveform is or photon, anti-Stokes photon is generated only when there will be molecules or carriers in the intermediate state. But in the thermal equilibrium, the chance of molecules in the intermediate state is very less. So, the chance for production of anti-Stokes photon is less comparing to Stokes photon generation. So, this is the notes corresponding to the previous process, that is in Stokes process, incoming photon frequency Fp excites the molecules from the ground state to the virtual state, and the molecule returns to intermediate state releasing the Stokes photon of energy Fs, and the energy difference between the virtual and intermediate level is smaller than the energy difference between the ground and virtual state. So the frequency of the Stokes photon is lower than that of the incident photon. This is important thing. That means the frequency of the Stokes photon is lower than that of the incident photon, that is Fs less than Fp. Similarly, in the anti-Stokes process, the incoming photon of frequency Fp excites the molecules from the intermediate state to the virtual state. The molecule returns to the ground state releasing an anti-Stokes photon of frequency Fa. And here the energy difference between the virtual and intermediate level is smaller than the energy difference between the ground and virtual state. So the frequency of the anti-Stokes photon is higher than the incident photon. That is the thing. That is, frequency of the anti-Stokes photon is higher than the incident photon. And let us see a equation, that is energy difference between the intermediate level and ground level is delta E. See, energy difference between the intermediate level and ground is delta E. This energy difference is delta E. So in terms of Planck's constant, we can write a delta E is equal to H into delta F. So H into delta F. So H is Planck's constant, and we can write a Stokes frequency will be, we know that Stokes frequency, what is Stokes frequency? Stokes frequency will be Fp minus this frequency, right? Fs will be Fp minus this frequency is delta F. Therefore we can write Fs will be equal to Fp minus delta F, that is equal to Fp minus delta E by H, where delta is the vibrational energy, that is the energy corresponding to the molecule vibration. So in the case of Stokes generation process, this vibrational energy is delivered to the molecule. But in the case of anti-Stokes generation process, the molecule supplies this vibrational energy to the photon. So once a pump signal is given to a material, then in the case of anti-Stokes generation process, the molecule gives the vibrational energy to this pump signal so that its frequency will be increased. So that their energy will be increased. So when energy increased, frequency also will be increased. So in the anti-Stokes generation process, the molecule supplies the vibrational energy to the photon, incident photon. So this will increase the total energy of the incident photon so that frequency of the incident photon is increased. So the frequency of the anti-Stokes waves also increased. So in the case of thermal equilibrium, the density of the molecules in the intermediate state is much smaller than the density in the ground state. Therefore the number of the anti-Stokes photon is much smaller compared to the Stokes photon. Let us see the Raman scattering in the case of optical amplifier. See, in the case of optical fibers, it shows a Raman scattering. Suppose when we are giving a signal to the optical fiber cable, some of the signals may be scattered due to Raman scattering effect. And this that means this, in the case of optical fiber, Raman scattering will take place over a large range of frequencies. And the energy conversion process between the pump and the Stokes waves is characterized by a parameter called Raman gain, that is GR. See, basically in the Raman scattering process, there is an energy conversion takes place between the pump wave and the Stokes wave. And Stokes wave is produced due to the Raman scattering process. So the energy conversion process depends upon the parameter, that is Raman gain parameter GR. Basically this Raman gain depends upon the material composition of the fiber core and the dopants inside that fiber. And the figure shows the typical Raman gain spectrum of the silica glass fiber, and you can see that here a maximum gain occur at this point, that is between 9, here it is in frequency shift, and this is the normalized gain, and here the maximum shift, there are different maximums, and there is a one maximum here, and also there are other minor peaks also here. Here when we are considering all the maximum peaks, then we can see that there is a total bandwidth of 40 terahertz will be there for this Raman there will be total bandwidth of 40 terahertz for this Raman amplifier. And here you can see that for the first maxima, its bandwidth is between approximately between 9 terahertz to, you can see, suppose it is a 60 terahertz, 16 terahertz. You can see roughly from this figure, you can see it is a 16 terahertz, that is from 9 terahertz to 16 terahertz. And when we are considering all these, we can see that this Raman, in the case of Raman amplifier, the maximum Raman gain is approximately 20 dB when we are transferring it to dB value 20 dB. And here the wavelength where the fiber act as a Raman amplifier corresponding to 1550 nanometer wavelength. So this is all about this Raman spectrum or Raman gain spectrum of the silica glass. Next, we can go to the details of the fiber Raman amplifier. Up to this session, we have discussed about the Raman scattering phenomena and how this, that means we have discussed about the spontaneous Raman scattering and how the pump wave is transferred to Stokes or anti-Stokes waves we have discussed. Now, we will go to the fiber Raman amplifier, and for optical amplification in the case of fiber Raman amplifier, there should be stimulated Raman scattering. That means once there is stimulated Raman scattering takes place in the fiber, optical fiber, then it will act as a amplifier. So we can say it as a fiber Raman amplifier. We have discussed about this spontaneous Raman scattering, but it is not the takes place in the case of Raman amplifier. The basic principle of the Raman amplifier, fiber Raman amplifier, that means optical fiber to act as an amplifier, there should be stimulated Raman scattering takes place. So the basic difference between the stimulated and spontaneous Raman scattering is shown in the figure. You can see that this is the spontaneous Raman scattering and this is the stimulated Raman scattering. What is the difference seen here is that here there is only pump signal and there is a medium. Suppose this medium is an optical fiber cable. When pump signal is given, or when that pump signal passes through this material or optical fiber material, the light will be scattered out. As a result, it will produce Stokes and anti-Stokes waveforms. But it is shown that there is only Stokes wave because the chances of producing anti-Stokes is less. Because at thermal equilibrium, there will be larger number of Stokes waves produced. Similarly, the difference is that in the case of stimulated Raman scattering, along with the pump signal, there should be our transmitting original signal will be there. There should be other signal along with the pump signal. So both will go to this optical fiber cable or any type of medium. As a result, the light will be scattered out, and that light will contains Stokes waves and also pump signal. That means here in the medium, in the case of stimulated Raman scattering, there will be the presence of a signal along with the pump signal. As a result, at the output, Stokes waves as well as pump signal will be produced. So next we can go to the details of the Raman amplification process. Before that, if the intensity of the incident field is below the threshold value, particular threshold value, then there will be spontaneous scattering occurs. So in order to take place stimulated Raman scattering, the intensity, there should be a particular intensity for the input signal, and that value is called a threshold value. And before that threshold value, spontaneous scattering occurs, and above that threshold value, stimulated scattering will occur. Stimulated Raman scattering will occur. And stimulated Raman scattering can be used for the light amplification process. Suppose if a small signal at stop frequency is present along with the pump signals, then the signal gets amplified while retaining all the characteristics of the input signal. That is what is occurring in the case of amplification process. Let us see it in detail. Suppose there is an optical fiber cable here, and there should be some molecular vibration in this optical fiber cable. We are using silica fiber as a core material in this case. Silica glass is the material. And suppose we are transmitting signals at frequencies at wavelength. Suppose this is wavelength axis, and here this fiber is transmitting different wavelengths such as 1550 nanometer, 1500 nanometer, 1450 nanometer, etc. that is passing through this fiber. And if we are giving a high power signal to this molecular fiber, that means suppose this is a pump signal, let us call it as a pump signal, it will be a high power signal. When we are giving this signal to this, and suppose the wavelength of this pump signal is 1300 nanometer, and you know that there is some molecular vibrations in this fiber, and once this signal is passing through this fiber, it will interact with this molecular vibration, so that some of the energy, these molecular vibrations will be, the energy will be absorbed by these molecular vibrations, so that the energy of this pump signal will be reduced due to this molecular vibrations, so that the signals will be scattered in this manner. And this, due to this energy loss, you know that energy is equal to h nu, that is energy is directly proportional to the frequency, but it is inversely proportional to the wavelength. Due to this energy loss, the wavelength of the incoming signal will be reduced. So once the wavelength is reduced, means that is, suppose now it is 1300 nanometer, after this scattering it will be 1550 nanometer. Okay, so when it become 1550 nanometer, we know that there is already the signals present, 1550 nanometer signal is present here, right? Already this optical fiber is transmitting the wavelength of signals like this, and along with we are transmitting this pump signal, and this pump signal has a high energy, and when it interact with this molecular vibrations, its energy will be lost. Due to this losing in the energy, its wavelength will be increased. So you can see that now its wavelength is 1550 nanometer. That means this 1550 nanometer is already present in the fiber, right? That means this 1550 nanometer energy is increased, or it is strengthened. So in the case of optical fiber, optical Raman amplifier, amplification takes place in this manner. That means there is no population inversion, or there is no lacing action. Here amplification takes place due to the process of stimulated Raman scattering. You know that there is a presence of original signal here, and that signal should have some threshold value, and once the pump signal is going through it, this pump signal will produce another frequency or another wavelength, and if that wavelength is already present in this original signal, then that signal will be strengthened or amplified. So 1550 and 1550 will be there. So this will strengthen this component, this frequency shift, that is here this pump signal shift the frequency. So this frequency shift will strengthen or amplify this signals originally present in the optical fiber. As a result, amplification occurs in this case. So the points you should note here is that there should be some threshold level for the signal to occur Raman amplification, and also the input pump signal should have high power, and also in the case of Raman amplifier there is no population inversion process and all, and also you can see that here the signal component, that means we have said that here if a small signal at Stokes frequency is present along with the pump, then the signal gets amplified. That is the process taking place here. That means here the main thing is that there is a Stokes shift occurs. Stokes shift means that here the wavelength is shifted to this point. That means frequency is reduced. So there is a Stokes shift occur due to the stimulated Raman scattering. Here is a scattering process, and that is in the presence of some signal. That is why it is called stimulated scattering. So this is the things that we have noted in the case of stimulated Raman scattering and Raman amplification process. So the differential equations governing the intensities of the pump and Stokes waves are dIs by dz is equal to gr into ip into is minus alpha s into is, where is is the intensity of the Stokes signal and gr is the gain of the Raman amplifier, and IP is the intensity of the pump signal, and alpha S is the attenuation corresponding to the stock signal, and IS is the stock signal intensity, and omega P is the frequency, angular frequency corresponding to the pump signal, and omega S is the angular frequency corresponding to the Stokes signal. So this is the differential equation governing the pump signal and Stokes signal. And if, we know that there should be some threshold value for the pump signal, and therefore the threshold value for stimulated scattering occur is given by IPTH is equal to alpha S by GR. So the threshold value for stimulated scattering is defined as the input intensity IPTH value of the pump for which Stokes waves show gain in the fiber. That is the definition for the threshold value for the pump signal. So we can say different Raman fiber amplifier or fiber Raman amplifier configuration with the different pumping. There are two types of pumping can be used. This is co-directional pumping, this is counter directional pumping. In the case of co-directional pumping, pump signal is applied in the same direction as that of the original signal. See, this is the original signal, and the pump signal is applied in the same direction as that of the original signal flow, and these two are coupled to the fiber, and these two signals are coupled to the fiber using a coupler that is shown here, and then it is coupled to this fiber. When the signal passes through this fiber, it will be amplified due to stimulated Raman scattering effect. Similarly, when the pump signal is applied in the counter direction as that of the signal, so these two are coupled using this coupler. Here the difference is that pump signal is applied in the opposite direction to that of the signal. Once it joins each other, and then it will be passed through the fiber, and stimulated scattering, Raman scattering occurs in the fiber, and the signal will be amplified due to this stimulated Raman scattering. As a result, stock shift will be occurring in this. As a result, signal will be amplified. Here there is no lacing action takes place in the case of fiber Raman amplifier, and also since there is no lacing action, there will be lesser chance of amplifier spontaneous emission noise, and usually the gain of this Raman amplifier is 20 dB, and here the requirement is that we have to apply giant pulse for pulse as pump signal in the case of this Raman amplifier. And here you know that there is no population inversion in this case, so we can say that it is a non-resonant amplifier. That's all about this topic. Thank you.